All right, so welcome to my first lesson on factoring, entitled Common Factors. So for the next few lessons, we're going to be talking about a mathematical process called factoring. Actually, a word that you've probably seen before when you're talking about greatest common factor, or GCF. I'll come back to that concept in just a second. So we say that numbers that share a common factor are divisible by some common number. So the key is divisibility. For example, 4 and 8 both share a common factor of 4 since they're both divisible by 4. So here's the demonstration, the big yellow box. 4 is 4 times 1, and 8 is 4 times 2. 4 is a basic building block for both numbers. You'll notice that between 4 and 8, they also have a common factor of 2, because 4 is divisible by 2 and 8 is divisible by 2. And they also have a common factor of 1. Now, we choose really not to ever mention common factors of 1 because two numbers always have a common factor of 1. Anything is divisible by 1, so that has to work. So we tend to say that 4 is the GCF because it's the largest of those numbers that would be a common factor. So we call 4 the greatest common factor out of all of those. So we learned that in maybe our grade school days, and we kind of put it on the shelf, we forget about it, but the same principle also applies to variables, and we've been talking about that for the past little while too. Consider y and y squared. Those are both also divisible by y. They also both have a common factor of y. And again, we break it down in the yellow box here that y is y multiplied by 1, and y squared is y multiplied by y. So you can see when we break it down as a product, y pops up as a product. So you can notice again that y squared divided by y does give you y. Y squared is divisible by y. But its result, though, is y to the power of 1. So here's two quick checks for understanding. I've got here two numerical terms, 10 and 50, and I'm going to ask you what are the common factors between 10 and 50? Well, you're going to have to look at both of them and sort of say to yourself, what can I divide both of these terms by nice and evenly? The answer, well, there are a few actually, right? So 10 and 50 are both divisible by 2. They're both even numbers, so 2 is one of those possibilities. But if you think about it, they're both divisible by 5 as well, because they both end in zeros. So 5 is another possibility. And let's not forget 10 itself, right? 10 is divisible by 10, and 50 is divisible by 10. So 10 is another possibility. I mean, I guess, I mentioned, yeah, 1 is a nice little throw-in that we usually put in there, but it's so small, and any pair of numbers has a common factor of 1. So we tend not to really mention the 1. 2, 5, and 10 are your best, and 10 would be the GCF between 10 and 50. If you consider 2xy and 6x for a moment, right, we've thrown in some variables here, so let's think about both the numbers that are in front, the coefficients, and the variables themselves. Well, let's compare 2 and 6. What's the GCF between 2 and 6? Well, 1 is a common factor, but again, we don't tend to mention it. What about 2? Yeah, they're both divisible by 2, and the buck kind of stops there. Then when we look at the variables, well, let's ask ourselves, is there an x in both terms? Well, yeah, both of them have an x term, so x is a common factor. We don't go any higher than x. We don't put x to the power of 2 because there's only one x there and there's only one x there. Then we go on to the y, and we notice that, well, there's no y's attached to the second term, so y isn't a common factor. So 2x is actually the GCF of both of those terms. Okay, so hopefully that makes sense to you. All right, so let's get on to the actual title of the lesson today, to common factor a polynomial. So we've been talking about polynomials. That means several terms. And to common factor, that's the title of our lesson today. So if we're going to be common factoring a polynomial, we're going to need to remove any common factors from all of the terms. That means both numerical and variable, just like with the last example there with the 2xy and the 6x. So we're going to take that common factor out of each term. We're going to divide it from each term and basically write down what's left over contained in a set of brackets. You're always going to want to take out the greatest common factor, or GCF, as I mentioned in a few of the examples, because that means to factor fully. Typically, your instructions is going to be to factor fully. For the purposes of factoring, we typically want to factor fully. I mean, with the last example, you had 2xy and 6x. To say just factor the 2 out would not be factoring fully. Factoring the 2x, factor it fully. And that'll be pretty clear from some of the examples that we'll see. This process, and this is a really big key to understanding, is that it's the reverse of expanding using distributive property. So let me just write down a quick expanding distributive property example. 2 bracket x plus 1. Distributive property says that if we take this 2 and we multiply it by each of the terms, it's the same thing as multiplying by the whole term, the whole binomial. So 2 times x gives us 2x, and 2 times 1 gives us plus 2. So common factoring now, I'm going to write it in green. Common factoring would be to take a look at both of these terms, the 2x and the 2, and say to ourselves, well, what number could we divide both of those evenly by? What's the greatest common factor? Turns out that the greatest common factor of both of those is 2. So the number 2 could be factored out of both of them, leaving you with 2 on the outside, and then on the inside of the brackets, x, because 2x divided by 2 is x, and plus 1, because 2 divided by 2 is 1. So what I've written here in green is factoring, and what I've written in here in blue is distributive property. So question A, if we're looking at both of these terms, we've got 10x and we've got minus 15. We've got a binomial. We've got 2 terms. So looking at both of those terms, the GCF of both of those terms, well, let's think about just sheer numbers, 10 and 15. Well, the highest number that we could pull out of both of them is 5. Okay? 10 is divisible by 5, 15 is divisible by 5. In fact, that's really the only common factor, aside from 1, that we could pull out of both of those numbers. Let's think about the x here for a second. Can we divide x by the first term? Well, yes, we could take 10x and divide it by x. But the second term, 15, well, we can't really divide it evenly by x because there aren't any other x terms to sort of take out of it. Okay? So what's left over is in the brackets. So we ask ourselves, what's 10x divided by 5? Well, 10x divided by 5, 10 divided by 5 leaves us with 2, and we didn't divide by x, right? So there's still an x hanging out on the side there. Let's consider the minus in the middle. 15 divided by 5. So 15 divided by 5 winds up being 3. So if you want to try question B without my help, pause the video now, or if you want to keep going, let's take a look at question B. So with question B, we no longer have any numerical values that can be factored out, right? The coefficients of both of these is 1. So realistically, yes, we could write the 1 down, but we all know that 1 distributed doesn't change anything. So there's no sense in trying to factor out a numerical value. But let's consider the x cubed here. X cubed and x. Well, how many x's can I divide? Well, I can divide a total of 3 x's out of x cubed, but I can only divide 1 x out of x to the power of 1, right? So the most x's that can be taken out here is x to the power of 1. Moving on to the y values, I have y squared. The most y's that I can take out of y squared would be y squared, and the most y's that I could take out of y cubed would be y cubed. So the most that I can take out of both terms would be y squared. What that leaves me with is, I'll draw my brackets in advance, I've taken one of the x's out of x cubed, that leaves me with x squared, and I've taken both of the y squareds out of the y squared. So I'm left with no y squareds, or y to the power of 0. You should remember that y to the power of 0 is actually just 1, right? If I wrote a 1 there, it doesn't need to be written, right? X squared times 1 is just x squared. Moving on to the second term now, I took that x out, so there aren't any x's left in front of that term, and I took 2 of the 3 y's that were represented in the second term. So I'm left with just a y. And again, you know, maybe if I scratch this out in red on the side, we can actually see the distributive property in reverse here. So we've got x, y squared, bracket x squared plus y. Distributive property says that if I take this entire term and I multiply it by that first term, I should get the first term. X times x squared is x cubed, and y squared times no other y's is y squared. We're going to take that term and multiply it by the second term now, which is just y. X times no other x's is going to be plus x, and y squared times y is going to be y cubed. And you can see that this that I've written in red matches this that was the original question, okay? And that kind of proves again that my factoring worked. So everything that I've written in red here is not part of the solution. It is part of the checking because it works, okay? So that would be factored fully in green. So we're looking at a trinomial this time. We have 3 terms, and the greatest common number that I can take out of all 3 of those terms is the number 2. So I can get the number 2 out of both of these. So I'm going to write the 2 down. And in terms of the variables, I've got an x squared, an x, and an x cubed. The greatest x term that I can take out is just x because that's the highest, right? I can't take out x squared because I only had 1x there. So I'll just take out 1x. Once I've taken out 2x, I'm going to see what I would get left. So I'm left with a 2, and I'm left with 1x here. The second term is a bit awkward, because if I divide minus 2 by 2, I'm left with minus 1. I'm going to write it for now, because x divided by x is also 1. So I'm not left with nothing, even though 2x is on the outside. I'm left with minus 1. It's kind of like a placeholder. We divided 2x by itself, so 1 is left in its place. 8 divided by 2 is going to be a 4, and x cubed, if I took one of the x's away from it, would leave me with x squared. And that, again, is factored fully. I could check it just like I did up here in red by doing distributive property, but not going to do that. We're going to continue. All right, so now let's move on to question D. Question D is a little bit tricky because you kind of have to look really closely with those coefficient values. 24, 18, and 12 on the surface are all divisible by 2. So I guess you could say, yeah, I'll take a common factor of 2 out, but be careful. 2 isn't the greatest common factor, okay? So try to look for a bigger number. Now, could I take 3 out of all of those? Well, yeah, 24 is divisible by 3, so is 18, and so is 12. But if a number is divisible by 2 and it's divisible by 3, there's an interesting property. It's also divisible by 6. So 24, hopefully you know, is divisible by 6. 18 is divisible by 6, and so is 12. Can't really go higher than 6, though, right? They're not divisible by 7. They're not divisible by 8. And they're not divisible by 9 or 10 or 11 or even 12. Because if you think about it, 24 is divisible by 12, and so is 12, but 18 is unfortunately not divisible by 12. So the buck kind of stops at 6. Okay? Now looking at the variables, this is almost identical to what we did in question B. Let's think about the m terms. So I've got m cubed here, I've got m power of 2 here, and I've got m all by itself. Well, the greatest common factor I can take out of all those is plain old m. Taking a look at n squared, I've got n cubed, and I've got n squared. The greatest common factor out of all of those I can take is not just n, but n squared. Because I've got n squared there, I've got n to the power of 3, which is bigger here, and I've got n squared there. Last part, you start your brackets off, and you write your leftovers. So if I take 6 out of 24, 24 divided by 6 is 4. If I take one of the m's away from m cubed, I'm left with m squared. And if I divide n squared by n squared, I'm left with no n's, or n to the power of 0, which is basically, again, just 1. I could write a 1 down there, but we all know that multiplying by 1 leaves it the same. I could divide 18 by 6 to get the next term. That gives me 3. If I took m to the power of 2 divided by m, I'm left with m to the power of 1. And if I take n cubed and I divide that by n to the power of 2, I'm left with also n to the power of 1. Final term now, negative 12. Don't forget that minus there. Negative 12 divided by positive 6 leaves you with negative 2. M divided by itself leaves you with m to the power of 0, which is 1. And again, we're not going to write 1 times 2. And n squared divided by n squared is also n to the power of 0, which is 1. And we're not going to write negative 2 times 1, because that would be redundant.